Much of our discussion in this class is going to revolve around motion and the description of motion. And this is actually a branch that we call kinematics. So we have here kinematics. Kinematics is the description of motion without paying any regard to the forces which cause it. That is a different branch called dynamics that we'll discuss in chapters 4 and 5 and beyond. But the first thing that we have to do before we can discuss motion is we have to give some sort of a frame of reference for our motion. It doesn't make sense to talk about motion if we have no standard to discuss it within. So we could here, take these people riding on this bicycle here in this picture. We could take a coordinate system and we could define a coordinate system to be like this, in which case I have a positive x here to the left and a positive y going upwards, and these people would be moving in the positive x direction with some sort of velocity. However, if and they would probably all have roughly the same velocity. If I were instead to give a coordinate system and I were to place this coordinate system on this girl in blue, then she would have, within this coordinate system, she would have no velocity because the coordinate system itself is moving with her. And relative to her, this guy over here would have zero velocity as well, because as she's biking along and she looks over, he would always be there. And so the velocity within that coordinate system of him would be zero because he is moving along also with the coordinate system. So where we place our coordinate system is very important. Most of the problems that we do in this class, most of the exercises are going to use a reference frame which is maybe on the surface of the earth. And so that way, let's say we throw a ball or something like this, then that ball has some velocity relative to the surface of the earth. But in reality, if we chose a reference frame outside of the earth and we look back, we would see that everything on the surface of the earth is actually moving very, very quickly, over 1,000 miles an hour actually. If we were to have our coordinate system out of the earth. So having where we place our coordinate system is very important. We have to have a frame of reference for our motion before we can even begin to discuss motion. And the direction in which we call positive and negative is very important as well. We usually define our coordinate systems, just like you have a Cartesian coordinate system like this, x and y, and we could even have a z, which may go into or out of the screen here. Once we've defined our coordinate system, we can talk about motion within that coordinate system. So here, this figure on the left, we have a traditionally defined coordinate system with a positive x going to the right and a positive y going upwards. And we talk about a change. So we have this teacher here, and she walks over to the right. We talk about her change in the x position here. And let me go ahead and talk about some notation here for a minute. This triangle symbol that you see, this is a Greek letter delta. It is a uppercase delta from the Greek alphabet, and it means change. A change in something. So we have, it's always your final minus your initial. So we have here a delta x would be read change in x, and this is always equal to some x final. So some final x position, x coordinate. This x refers to a coordinate. Minus some initial x position. Okay, sometimes we could see this is x2, so 2 being our second position, minus x1, 1 being our first position, or sometimes we might just write it as x, so some position at some time, minus x sub 0. And this is really, you can think of this, this is just at any later time. There's no subscript there, just some later time dependent on when we're analyzing. And this 0 is really at time equal to 0. This is often referred to, this here we say x naught. So that's just the colloquialism that we have for it. But x sub 0 is x at time equal to 0. It's the same as our x initial, or maybe x1, and we often read as x naught. So defining our coordinate system up here with a positive x being to the right, if she started over here when we started the clock, she started over here at x naught, an initial position of 1.5 meters. And then she moves over. We have some x final, or we could just say x is 3.5 meters. Then her change in x, this delta x, is the final minus the initial, which is a positive 2 meters. And so in our coordinate system, the fact that she moved 2 meters, a positive 2 meters, means that she moved 2 meters to the right. Using the same coordinate system over here in this figure on the right with the guy on the plane, we again have a traditional coordinate system. And he started out in this chair over here, and then he walked to the back of the plane. And so his change in the x coordinate, change in the x position, was a negative 4 meters. He started over here at x naught was 6, x final was 2, and remember, delta is always the final minus the initial, so we have here the x final minus x initial is the 2 minus the 6, so it's negative 4 meters. And so in this coordinate system, a change in x of negative 4 indicates that he moved 4 meters to the left. If I were to flip around these coordinate systems, so if let's see here. If I were to flip these coordinate systems around, so that way I called a positive, let's get rid of this, a positive x is to the left, get rid of this one here. So if I call a positive x to be to the left, then the lady's change in the x position would have been a negative 2 meters. So in this case, delta x is equal to negative 2 meters. And then in this case, the guy on the airplane, his delta x would have been equal to a positive 4 meters. So it doesn't make any sense to talk about a change in position without a coordinate system. In both cases, so when I flip this around, the fact that negative was to the left, and a positive was to the left, and she moved a negative 2 meters, it means that she moved to the right. So she moved to the right in either case. One was positive, one was negative, depending on the coordinate system. He moved 4 meters to the left, regardless of the coordinate system here. It's just that when I had a coordinate system with a positive being to the right, he moved a negative 4 meters. When the coordinate system was positive to the left, he moved a positive 4 meters. Either way, he was still moving to the left. Some other notation, as I introduce velocity and acceleration and things like that, we'll continue to use this notation, this algebraic notation. So we'll use for velocity, we'll use a v, and so we have things like v initial is the same thing as v naught. And we also have here v final, which really just means the same thing as some other v later on. We also have delta v is equal to v minus v naught, or we could say this is the same thing as v final minus v initial. As we go through and we talk about acceleration, which we use a. This is going to be, and by the way, these are actually vector quantities. So is delta x. This is actually a vector as well. We have here a initial. It would be the same thing as a naught. Or we have a final, would be the same thing as a, or delta a would be a final minus a initial. Although for 95% of all the problems we do in this class will have a constant acceleration, so a lot of this won't come into play later on. It'll just be kind of more dealing with this stuff with velocity and also with the delta x. But we also have, we can apply this delta notation to anything. We can talk about delta t as well. So a change in time would be delta t, and this would be like time final minus time initial. But oftentimes we'll just consider the initial time to be equal to 0. And that way delta t is just whatever the final time was. So it'd be simple there. But none of this makes sense. Talking about positive velocity, positive acceleration, negative velocity, negative acceleration, none of it makes sense without a coordinate system. A lot of the stuff we will do will stick with a traditional coordinate system with a positive x to the right and a positive y upwards. But there are times that we may want to have a coordinate system flipped around. So we have like y down like this, x like that. We could even, if we wanted to, we could flip these around and say this is x, this is y. Later on, I think that we'll find that it'll be helpful to have coordinate systems like this. So x is this way, y is that way. We can change it around to find it however is most suitable for the problem that we're working on. But we have to define a coordinate system, otherwise the numbers we get don't make sense.